So good afternoon, everyone. Welcome to the series of webinars from the PPG's program. So today we have the pleasure to receive Professor Thomas Peron from ICMC-USP. Professor Thomas is graduated in computational physics and has received his master and PhD degree in applied physics. His main research interests are the study of complex systems, has dynamics on graphs, and complex networks. So thank you again, Thomas, for accepting our invitation for this seminar. And the floor is yours.
Okay, thank you, Andressa, for the introduction. And thank you all from the PPG's program for inviting me to give this talk. So today, I'll be talking about network process on clique networks with a high average degree. So what does this mean? So what we'll study here is we'll study networks, but these networks, they are a bit special. They are constructed in a special way. They will be made up of cliques, and cliques are subgraphs that are fully connected. So these fully connected subgraphs will be some kind of building blocks for our networks. And what we will show is that when we consider dynamical processes happening on these networks, we'll see that the performance of this dynamical process will be equivalent as if we had networks that didn't have these cliques. In other words, we will show that if we have a highly clustered structure, so a network with many triangles or many cliques, the performance of a dynamical process doesn't depend on this clique structure. So this will be more clear throughout this talk. And yeah, okay, this joint work with Clara Steghuis from the University of Twente in the Netherlands. So, but before I talk about our work, let me give some motivation for the question that we address here. So if you take the papers on in the literature that we call network science, especially in the early days of network science, well, you'll probably read sentences like this. Okay, we want to study the relation between topology and dynamics, and we hope that this helps us to understand the dynamics of real-world networks or real complex systems that are modeled with networks. So what are the type of questions that people address in this context? So usually one has a network. So a network is composed of many nodes, and these nodes interact with each other via links or edges. And these networks can be, for example, one node can be, networks can be social networks in which the nodes are persons and the links are some kind of relationship that these persons have. Or we could have the internet or technological networks like power grids, in which the nodes are power stations and the connection are transmission lines. And every complex system or every network, it has a relevant, usually has a relevant dynamical process associated to it. For example, what are the most common dynamics that people study over networks? So we have dynamics happening on a network. There could be percolation, in which we remove nodes or edges with a certain probability. Percolation process can be used to model the stationary behavior of epidemic spreading, or it can, via studying a percolation process, we can have an estimation of the number of infected people at the end of the epidemic. Other relevant processes are epidemic and rumor spreading. Perhaps it's needless to say how important epidemic spreading was in the last couple of years. There has been a bunch of papers investigating how COVID could spread over social networks. So this was a very highly popular topic, research topic in the last years. And all the machinery that was developed on network science since the early 2000s, everything was applying this more sophisticated studies that aim at investigating the spreading of COVID in real social networks. And we could also have another context, the case in which the nodes are oscillators, nonlinear oscillators, and these oscillators interact via complex network. Then the question in this context would be, okay, what is the arrangement of how can we wire these oscillators so that they can oscillate in synchrony? So these are the type of questions and the type of dynamical process investigated in the literature. And usually the goal is to, okay, depending on how the topology is organized, how the dynamical process will, what will be the performance of dynamical process given a certain topology, a certain structure of these connections. And the most common methodology, so to speak, to tackle these problems is to consider random networks, because we can model random networks, we can deal analytically with random networks, and that's okay. But there is one minor inconvenience, so to speak, which is the following. If we create a random network, and that could be via, for example, an Erdős-Rényi model, on which we connect these nodes with a fixed probability. If we generate a random network like this, or via a configuration model in which we specify any degree distribution we like, if we generate a random network in this with this methodology, and we take a zoom in the local topology of the nodes, so as I show here, we'll probably see a structure like this. So something that resembles a tree. So we have the nodes, but the nodes have neighbors, but the neighbors of these nodes, they are not neighbors among themselves. So the local topology will be very similar to a tree. So we say that random networks are locally tree-like in this sense. On the other hand, if we take now real networks, we'll see something very, very different. So if we take, for example, social network, like the network of, if you take the network of your Facebook friends, or the Twitter or something like this, you'll probably see a structure, a very different structure. So we'll probably see the occurrence of triangles, or other types of subgraphs in which the triangles overlap each other. And not to mention other types of properties like degree-degree correlations, in which high-degree nodes tend to connect to other highly connected nodes, or low-degree nodes connect to very highly connected nodes, like how it happens in the internet. So many websites connect to Google, but yeah, Google has many neighbors, but the neighbors, the websites that cite Google, they most likely not cited as Google. So we have the presence of hubs, and also modular structures. So there could be many networks have these, they can be divided into modules in which these, what we call communities, they are they're more connected within themselves than with the rest of the network. So then we noticed that there is some kind of gap between what we'll study, what we study, and what we want to model. So there is some kind of a gap in the structure of between the structure of random networks and real world networks. So given this gap, so then we want to answer the following question. Okay, so what would be the effects on the network dynamics of the simplest subgraph that we find in real networks, but is absent in random models? And this simplest subgraph will be triangles. So random networks do not have triangles, and real networks, they do have these special types of subgraphs. And then what will happen if we include these structures in a random graph model and then analyze dynamical process on these random models? And what will happen if we systematically vary these triangles, keeping other properties fixed, what will happen with a dynamical process? We will find a difference between the dynamics of clustered and non-clustered networks? So this is the a big question that we want to answer here. But then how can we answer this question? Well, first we need to select the dynamics. In this work, we'll deal with bond percolation, which is the following process. It's simply the process in which we randomly remove edges. So, for example, consider 1 minus p the probability of removing an edge from the network. Well, if this probability is 0, then we don't remove anything from the network, and the network remains intact. If we start to increase this probability, like for example 0.5, then it's very likely that some of the edges of this network will be missing. And then at the end of this process, one quantity that is interesting to monitor is the size of the giant component. So the size of this of the component of the largest component that remains connected after this percolation process. And then if we keep increasing this probability, then it's very likely that the network will be completely destroyed after it. And then the interesting quantity to monitor, as I said, is the size of the giant component, and usually one analyzes it as a function of this probability p. And it has a very very typical behavior for in traditional random graph models. It has this typical signature. For example, we have this transition for as we vary pi. So the size of the giant component until a certain critical probability will be 0, all the network will be the nodes will be isolated in very small components. But after a certain yeah.
I'm sorry, I'm not an expert in this, but I'm trying to understand that. Please tell me that this probability for each edge, it happens to remove or not with probability 1 minus pi independently. So
independently, yeah.
Is that what is happening from the first picture to the second?
Exactly, yeah. Yes.
But when 1 minus p goes to 0.2, should it not have more edges than in the picture in the middle?
More edges than a picture in the middle.
Because it's closer to 0, right? So when 1 minus p is 0.
Oh yeah. So yeah. I'm sorry. So that it's. I think so there should be So I think I switched it.
I definitely have no idea. I honestly asking.
It makes sense. Yeah, it makes sense. It should be the central panel.
0.8 probably.
Yes. I wrote wrongly the numbers. Yeah. Thank you.
Okay. Thank you.
Yeah, there should be a higher value in the right panel. Yeah, thank you. Yeah.
Okay, thank you.
So, although there could be some statistical fluctuations. This is just illustrative example. Yeah, but yeah, thank you. Yeah. So then, as we increase this, there should be a higher value here. Instead of 0.2, there should be a 0.6 or 0.8 to make more sense the picture. Thank you, Michelle. So as we increase the probability pi, then it's more likely that we have a higher largest component. So this is the size of the giant component as a function of the probability pi. Typically has this type of signature, or this type of curve. So then what we want to see is, okay, given that we have triangles in our network, how these triangles will impact on this dependence of the size of the largest component as a function of pi. And we will compare to networks that do not have triangles. So that's the problem that we are investigating here. Okay, so but we want to do some calculations. We want to approach this problem analytically. So, but how do we do this if traditional random network models do not have triangles, or if they are locally tree-like? Well, there are some ways to do that, but before I show the specific way in which by which we generate these random networks, I will show very briefly other models so that you can have some general idea how these more sophisticated configuration models work. So in the standard configuration model to generate random networks works as follows. So we set some degree distribution pk, some probability distribution pk, and from this distribution, with this distribution, we generate a sequence, a degree sequence, and each element of this sequence will say how many connections each node will have. So the first element of this sequence, okay, we'll say, oh, the first node has K1 connection, so then the second node will have 2 connections, and so on. So then after we have the sequence, we will match these potential connections accordingly, and then we construct our random network. However, if we calculate what we call the transitivity or the cluster coefficient, we get this expression. This quantity quantifies how many triangles we have in our network. So if this T is 1, it means that we have the fully connected graph. It means that all my neighbors, they are neighbors among themselves, or all my friends are friends among themselves. If this T is 0, it means that my friends are not friends among one another. Okay, that's what we call the transitivity or the clustering coefficient. It somehow measures the propensity to find triangles in our network. Well, if you have a random network construct with the standard configuration model, we can calculate this analytically, and what we'll find is this expression. T will depend on 1 over n, and these terms in the brackets are the moments of the degree distribution. And the degree distribution is just the probability of find a node with a certain degree. So it will depend on the size of the network. So if we consider larger and larger networks, this transitivity will go to 0. So this is, of course, not a good model to investigate the effects of triangles. So that's why what we say that these networks are locally tree-like. But so in order to generate clustering in random networks, there is another model called the Newman-Miller model. It was independently proposed by these 2 researchers. And in this model, we first define a joint probability distribution from which we derive 2 degree sequence. In the first sequence, this first sequence, it will say how many single edges each node will have. And by single edge, I mean edges that do not participate in triangles. They only connect one node to another, and there is no triangle involved. But we'll have a second degree sequence saying how many triangles each node will have. So for example, the first element will say it's T1. Okay, so the first node will have 2 triangles, the second node will have 3 triangles, and so on. If we match these degrees accordingly, then we can generate a network that has triangles. So then we can generate networks that have triangles. We can work with them analytically, and we can then calculate the dynamical properties that we like. But this model also has some sort of limitation, which is if we calculate the transitivity, we'll see that, well, this transitivity doesn't depend on the number of nodes. However, this in principle, it's good because as we increase the size of the network, we see that it doesn't depend on n anymore. So in the limit of large networks, this C will be constant. So that will be good because this means that the network has triangles, and then we can investigate the impact of triangles on the dynamics we want. However, the maximum level of clustering that this network has has an upper bound. It will be 1 over 1 plus the average degree. So it has an upper bound, but the level of clustering has an upper bound. And so then the effects of triangles that we want to see will be somehow limited. So we want to go beyond this limit. And even so, we are not going to use this model, but although we are not going to use, I wanted to show you just to give an idea how can we generate clustering in random networks. So now going to our problem, do triangles affect network dynamics? And we want to, as I said, we want to study this on a network that goes beyond this level of clustering generated by the Newman-Miller model. So, so which model we're going to use? So we will use a model in which we can have a higher number of triangles. And if we have a higher number of triangles, then we assume that the impact of these triangles will be stronger in our bond percolation dynamics. So in this model we are going to use, each node will have a degree vector. And this vector is defined as follows. So the first element will say how many single edges this node is attached to. So here, so the node A, it has two single edges. So then the first element is 2, but then it belongs to one triangle. So the second element is 1, and it belongs to one clique of order 4. So this is what we call the order of the clique. So it belongs to a fully connected subgraph of 4 nodes. That's our definition of clique. So this third element will be 1. And another example is the vector of this node B. It will have, it doesn't have single edges nor triangles, but it has one clique of order 4 and one clique of order 5. So then by generating these sequences of vectors of degree, we can specify how many cliques each node will have. And then we construct our network, and well, we can set distributions for these cliques, and then we can analyze these our dynamical processes analytically. So that's what we are going to do now. And remember, our question is, given that we have a network with many cliques, we want to see how a bond percolation process behaves on this network, and we want to compare with locally tree-like networks. Okay, so let's now our goal is to calculate the size of the giant component. But in order to do that, let's define some generating function. So the first generating function will be is associated to the degree distribution, this ki, which is the probability that a randomly chosen node is part of I k cliques. So that's equivalent to our degree distribution. And the second generating function is associated to this distribution here, I times ki over the average S. And this average S is the average number of cliques. This distribution is in the textbooks or in the papers in network science, they call this the excess degree distribution. And it's the probability that we randomly select an edge in our network, and at the end of this edge has a node with degree k. So it's a different distribution from the degree distribution. So then we define these two generating functions. And another important quantity that we need to define is U. We say that is the average probability that a node is not connected to the giant component. And another very important property for us here is H of kj pi. And it's the probability that a given node of k cliques is connected to j other nodes of the clique at pi larger than pi critical. So after the percolation threshold, that's the probability of a node is connected to its neighbors in a clique. Okay, so now we want to, in order to calculate the size of the largest component, first we need to, well, find a way to calculate this average probability. And then we can do this, the following we can use this toy example here and this subgraph I'm showing the right panel. Well, first we need to calculate, let's try to calculate the probability that a node is not connected to the giant component via one of its neighbors of a clique. Well, since it belongs to a clique, first we need to, let's say, well, we need to calculate the probability that this node is only connected to one of its neighbors in a clique. Well, this will be h, k, 1 pi. So it's the probability that this node is connected to only one neighbor inside the clique, times u, which is the average probability that a node is not connected to the giant component. But we also need to consider that this node is connected to two of its neighbors inside the clique. And also we need to consider the situation in which the node is connected to three of its neighbors, and so on until the size of the clique. So this is the probability that the node is not connected to the giant component via one of its neighbors inside the clique. Well, but this is only is related to only one clique. We need to average over all the possible cliques in our network. And if we average this over all the possibilities in our network via the generating function, this will be equivalent to the probability U. So this is we find a self-consistent way of calculating this average probability U. However, if we take this probability, the summation of j from 0 to k minus 1, and average over the degree distribution, we get the fraction of nodes that do not belong to the size to the largest component. Well, 1 minus that gives us the size of the largest component. So with that, so we have then two equations that we could, in principle, solve in a self-consistent way to see how the size of the giant component is changing as we vary the probability pi. Okay, so in principle, the problem is solved. But the problem now is that these equations are usually a bit complicated to solve. And yeah, for example, you could set random values to this probability U and for this probability H, and iterate this and find the curves, and then choose your degree distributions and perform all the analysis. However, yeah, it's difficult to get some intuition or insights if you don't have the explicit equations. So in order to have more in order to have some more intuition about the problem, we'll consider some approximation. So we will approximate these equations in the limit of large pi. So in the limit that the networks, the size of the giant component is large. So for very small u. And the reason that for which we do this will be clear in the next slide. So for large pi, so it means that u will be very small. So the average probability that a node does not belong to the giant component will be very, very small. If it is very, very small, we can Taylor expand the argument of GP. So we consider only the element 0, j equals to 0 and j equals to 1. And then we can write this approximation for the probability u. Then we need to calculate what is the probability that a node is disconnected from a clique. So it's when j equals to 0. Well, the probability that I remove an edge is 1 minus pi. And so if a node is completely disconnected from its clique, then it will be 1 minus pi to the power of k minus 1. Because, for example, if I have, if I belong to a 3 clique, then I have 2 neighbors, and the probability that I'm completely disconnected from this clique will be, well, 1 minus pi squared. Okay. So, and the probability to be connected to a single node in a clique, well, it will be the probability pi that I'm connected to at least one neighbor, and 1 minus pi to the power of k minus 2, because if I'm connected to one neighbor, then it remains there are k minus 2 other connections that I could have, but they need to be missing. So 1 minus pi to the power of k minus 2. And since this could be in k minus 1 ways, then I multiply by k minus 1. Okay, then with these two probabilities, I can Taylor expand GP again. And then I have this approximation for the probability U. So the equation looks a bit nasty, but and the approximation may sound a bit rough, but it will work. I will show you. Then we have the approximation for U, and we can do the same expansion for the size of the largest component. So that we have this very nasty equation. And now, since we know how to calculate everything, well, GP and G will depend on our degree distribution. And the degree distribution, well, this will depend on how we generate the networks. And that's what, now, since we have now some all the ingredients to calculate the size of the giant component as a function of probability pi, then we can start to perform some experiments. Okay. So now, since we have in principle all the information, let's consider the case of regular networks. So every node in our regular network is part of SK cliques. Okay, so all the nodes, they have the same number of cliques attached to them. So it's regular. And again, with 1 minus pi, we'll remove an edge. With 1 minus pi probability, we'll remove an edge. And S will be the size of the giant component. And in this case, the generating functions of the regular network will be given by this expression. G of x will be just x to the power of s, and GPS is x to the power of s minus 1. Okay, so but in order to compare the difference of, so remember what we wanted to do is compare the performance of these dynamics, the bond percolation, on a network that has clustering or has triangles, it has cliques, with networks that have that are locally tree-like. So what we're going to do is we'll generate networks with only K2 cliques, only with single edges. Then we will compare with networks that only have triangles and networks that only have 4 cliques. But of course, we'll keep some properties fixed. Okay, the average degree of all these networks will be the same. The only thing that will change over these networks is the number of triangles they have. And then we have this collection of networks. We'll perform the bond percolation dynamics and see how they differ from one another. Okay. So that's our first experiment. So here, one curve, it corresponds to networks that only have single edges. The other curve corresponds to networks that only have triangles, and this other one corresponds to networks that only have 4 cliques. And all the networks, all the nodes of all networks, they have degree, all the degrees are equal to 6. So the only thing that differs in them is the number of triangles they have in the structure. The average number of connections is the same. The solid lines are the solutions, the exact solutions of that self-consistent equation. And the dashed lines are approximation. We see that the approximation works very well with the simulation. The dots are simulations. It works very well with the simulation in the exact solution of the equations, and especially for a very large pi. And that's fine. That was the limit of our approximation. For very low pi, it doesn't work, but it doesn't matter right now. I will show you why we do this approximation in a moment.
Thomas.
Yes.
Just a question. What's the size of the network in this case?
Oh, very good question. The size of the network is 10,000 nodes.
Oh, 10,000. Okay. So it's a very small degree. So it's only 6, right? The average degree.
Yeah. The average degree is very small. Yeah.
Okay.
Compared to the size. Yeah.
Yeah,
so very good question. The simulations, they were performed with networks that have 10,000 nodes. You see, if the size of the network were smaller, like 1,000 nodes, probably we would see simulation points at values larger than 0 here for us. So that will be finite size effects that we say. But in order to minimize these finite size effects, then we bring the size of the network as large as we can. So yeah, the average degree is very small. It's equal to 6. And okay, what do we see in this picture? Well, for large probability pi, the size of the giant component of all networks, it becomes the same. So all networks reach a size of the largest component very close to 1. However, for intermediate values of pi, so we have some difference in their dynamical behavior. So these the networks that have the networks constructed with K4 cliques, they percolate we need higher values of this probability in order to percolate these networks. Percolated means that okay, the largest component starts to emerge, roughly speaking. Then so then for this case we can say that, well, the fact that we have triangles matters for our dynamics. So we can see some difference in the dynamical behavior of these networks. So this is what this picture is showing to us. However, if we now increase the average degree, we see that all the curves, they overlap each other. So before we had some difference between the percolation curves. Now we double the average degree is equal to 12, which you could say is still a relatively sparse network. But even though we have different levels of clustering or different levels of number of triangles, they behave dynamically dynamically the same. It doesn't matter. And this can be very surprising because you might think, well, having a high number of triangles, this could be well, something very important to my network or to my dynamical process. But even though we have a high number of triangles, my network behaves exactly the same as a locally tree-like network, a network that has topology just like the one generated by a random network model. So then, in some sense, you could say, well, then probably the differences that we observe in the dynamics of real complex systems, they could not be due to the fact that we have triangles, but to something else. Okay, now the reason that we calculate our approximation, there should be an expression here, but okay, it will appear soon. My mistake. Let me see. Okay, I will show now the experiment we do for the Poisson networks, and then I'll show the result from our approximation. Okay, so now let's say that every node is part of, on average, of SK cliques. So now the distribution of cliques follows a Poisson distribution. And now we perform the same experiment. With 1 minus pi probability, we remove an edge and calculate the size of the giant component. And now the the generating functions for the Poisson case, they are special. They're the generating functions GP and G, they are identical. And okay, now if we perform the same experiment, we see that for the Poisson networks that have average degree equal to 6 for all vertices, we see now that the size of the largest component converges to different values. Before, for the regular network, for large pi, the S went to 1 for all cases, but here, no, this doesn't happen. So we have some difference. You see that at the end of the percolation process, when we have a very high value for pi, so the networks that only have 2 cliques, they can reach a high number of nodes in the largest component. But the networks constructed with K5 cliques, they will be the size of the giant component will contain a lower number of nodes. It will be smaller, so to speak. Okay, but now if we increase, if we double the average degree, the distance between these curves decreases, so they approach each other. So again, so although the curves, we have a different behavior from the regular case, we observe the same tendency, which is as we increase the average degree, the difference between clustered and unclustered networks reduces. So the cluster networks start to behave more similarly to locally tree-like networks. And yeah, so here is the expression I wanted to show in the previous slide. We can calculate, we can estimate the order of the difference between the size of the largest component of networks constructed only with Ki cliques, for example, minus the size of the largest component of a network constructed with Kj cliques. And so the difference between, for example, the size of the giant component of a network constructed with single edges with 2 cliques and 2 K5 cliques will be of this order. It will depend, of course, on the size of the cliques, J minus I. It will depend on the probability of removing edges, 1 minus pi. But it will depend on D. And D is the actual degree of the nodes. So S is the number of cliques, and K minus 1 is the it's the type of the clique. So it will be the actual degree of the node. And then, okay, if we have a very high degree, when D is very high, so this term here will be very small. So that means that as we increase the average degree, this difference between the size of the giant components will be smaller and smaller. So that's why it's useful to calculate. Then we see explicitly that, okay, if I increase the average degree of my network, the difference we expect in the dynamics of cluster and cluster networks will be smaller and smaller. Okay, so, but when you see this, the difference between these curves, you could ask yourself, okay, so these curves, they have, we have one curve for networks constructed with K2 cliques, so that will be this upper curve here, and we have another curve here for when we have when we construct a network only with K5 cliques, and they are very different from one another in this example. So you could imagine, okay, so but is this difference that we observe between the curves really due to the fact that we have different cliques and not to the fact that we have different sequences? Because we cannot use the same sequence, the same degree sequence for a network that is for a network that only has 2 cliques and with a network that only has 5 cliques. So because when we have a network, for example, constructed with 4 cliques, yeah, we need to have a degree that is well proportional to 4 in order to construct a network. But here, when we have network with only 2 cliques, that's not necessarily the case. So then you could wonder, maybe the difference in the percolation of these networks could be due to the fact that we have different sequences, different degree sequences. Okay, so in order to test this hypothesis that the difference that we see is actually due to the different degree sequence that we have, we'll do the following experiment. So we'll construct a degree sequence by generating random numbers with a Poisson distribution with mean 1. So then we construct, we'll take this sequence and we'll multiply by 2, all this sequence. So we'll generate an array. If you're programming these networks, we'll generate an array, random array according to this distribution, and we'll multiply by 2. This will be the sequence that we would use to construct networks only with K4 cliques. Then we'll take the same sequence, multiply by 3, and then we'll construct networks that only have triangles. And then finally, we'll take the same sequence, multiply by 4, and that will be the sequence that we use to construct networks that only have 2 cliques. What we'll have in the end? We will have in the end networks that have the same, they have the exact same degree sequence, and the possible degrees that we'll have will be 0, 6, 12, and so on. So then we'll have networks that have the exact same sequence, but they will have different number of triangles. And then let's see what will happen if we construct networks and then run the dynamics on them. Well, what we see then is that the percolation curves of these networks are identical. So it doesn't matter if you construct the networks with K2 cliques, with K3 or K4, or if you have 1,000 number of 1,000, doesn't matter. If the networks have the same degree sequence, they will behave dynamically. The performance of the dynamical process will be the same. And indeed, if you see here, the simulation points match very well with the exact solution of those implicit equations, and also our approximation matches very well with this stationary value for the giant component. Okay, so if you calculate the clustering coefficient for this K4 network, that will be around 0.60, and the clustering coefficient for the K2 network will be very close to 0. So then, although this the transitivity level of these networks are very different, their dynamics is almost identical. Okay, so we are approaching the end of my talk, and I will show the one last example. Now we'll consider another type of dynamics, a more complex dynamics. We will consider that on top of each node, we'll place what we call a Coulomb multi-oscillator. So it's each node will be characterized by a phase that rotates with a certain frequency, omega-1i, and there is another coupling term with the other oscillators, and this coupling function will be given by the sign of the difference of the phases. And Aij here is the adjacence matrix. It will be 1 when the oscillators are connected and 0 if they're disconnected. And we'll do the same thing, take these networks that have the exact same degree sequence. We will run these dynamics and see what will happen. Just to give you an idea of the phenomenology of this model, when this K here is the, I didn't say that, K is the coupling strength, so how strongly each node feels its neighbors. And we can monitor these how the dynamics evolves with what we call the order parameter, which is just the average of these phasors on the complex plane. So basically, when the coupling is very low, the oscillators, they rotate incoherently. When the coupling is sufficiently strong, they all collapse. They group around a phase, an average phase, and they start to rotate with the same frequency. So then we have a transition between from an incoherent state to a coherent state, in the sense. Then, okay, when we run these dynamics on these networks, what we'll see is that the same pattern that we saw for the percolation case. So all the networks, even though they have different clustering patterns, they transition from a case in which the order parameter is very close to 0 when we don't have any coherent motion, and after a certain threshold, after a certain k is sufficiently strong, then they start to rotate in a coherent way. They start to rotate with the same frequency, and this transition is exactly the same for all networks. So it doesn't matter how much clustering the network has, it will behave the same as a locally tree-like network. Okay, so then answering the question that we posed in the beginning of this presentation, do triangles affect the network dynamics? Well, for bond percolation and also for this case of synchronization of Kuramoto oscillators, well, it will matter only when the average number of connections is very small. Okay, so yeah, so that was the main findings of our work. If you want to read more about the details of the calculations, you can check our paper. Thank you very much, and I'll be happy to answer any questions you may have. Yeah, thank you.
Thank you, Thomas, for your nice talk. So any questions for Thomas? So Thomas, I have two questions actually.
Okay.
The first one is, I realized that in these simulations, the average degree is always the same for all the vertices.
Mm-hmm.
So
yeah.
Do you have some intuition what happens if we have some kind of heterogeneous average degree for one vertex is a hub, another one has a small average degree? I don't know. Do you think it will change something?
Oh, okay. Yes. Yeah. Let me go back.
Mm-hmm.
Mm-hmm. So yeah. First, in the case of the Poisson networks, every node has on average the same number of connections, and then we see that then we have here the critical values for the emergence of the giant component. When we have, for example, power law networks, which is the case in which the nodes do not have the same average degree, then there will be an effect due to the size of the network. Because when we have the power law degree distributions, as we consider larger and larger networks, will be hubs that are more highly connected. So the maximum the degree of the hubs will increase with the size of the network. And what will happen is that the threshold here for the transition will be smaller and smaller. So that's one of the main one of the most prominent consequences of having hubs. So there is this result that when you have power law networks, that the power law exponent is between 2 and 3, the percolation threshold is in the limit of networks with infinitely many nodes, the percolation threshold will tend to 0. So that will be the impact of not having the same average degree for each node. In our paper, we calculate for the case for power law networks as well, but we consider networks with 10,000 nodes. And since we keep the size of the network, the networks always fixed, then the percolation threshold is finite, of course.
Okay, I see. Thank you. And my second question is about a model, because since you're interested to see, I don't know, some kind of triangle structures in the network, I was wondering about the exponential random graph model. I don't know if you know this model. So,
yeah.
Have you tried, or do you think it's interesting to explore this kind of percolation, this kind of model?
Oh yeah, absolutely. And in fact, with these exponential random graph models, I am not very familiar with them, but I know that you can generate these exponential random graph models by they're easier to, for example, you generate an ensemble of graphs by keeping certain properties fixed.
Yes, exactly. You fix a parameter for the number of triangles, for example,
yes.
And then you sample a graph.
Yeah, exactly. Yeah. So then you can you set, okay, I will construct my network with this number of transitivity, with this number of triangles, and then you sample them accordingly.
Exactly.
Yeah, you can do this with exponential random graphs. You can do.
Because I think it's interesting because you can see what happens when you change the parameter in the model. Because we have a parameter in the model to generate the, it's like the weight that you give for triangles, the weight that you give for stars, or whatever you want. So I think it would be interesting to see what happens when we change, or when you change the parameter, the parameter of this model.
Oh yeah, definitely. And in principle, it's you have more control. You can have a fine control of your transitivity, because then you sample what you want. Then you sample exactly what you want. I think when we were in another work, I considered working with exponential graphs, but at the end I switched to these configuration models simply because I found at the time that they were easier to implement computationally. That was.
I see. Where I mean, I don't know exactly what kind of software do you use, but in R, everything is implemented for exponential random graph. So
okay,
it's simple. Yeah, you can sample very easy.
Oh, that's good to know. I will take a look at that. Yeah, thank you.
Yeah, I have a work with exponential random graph. So if you want to talk about this,
please send me. I would like to take a look.
Good. So, any other questions for Thomas? Okay, so I think it's it for today. So thank you again, Thomas. It was a very interesting talk.
Thank you.